starch-based bioplastic films offers a biodegradable alternative to petroleum plastics. In this study, starch was blended with glycerol to form flexible films, which were evaluated for mechanical strength, water absorption and biodegradability. Results show that higher glycerol improves flexibility under soil conditions. Overall, starch-based films demonstrated strong potential for sustainable packaging application. Plastic pollution has become a major global problem due to the slow degradation of petroleum-based plastics. This has increased interest in biodegradable materials made from renewable sources. Starch is a widely available natural polymer that can be used to produce bioplastic films because it forms a good film structure when heated and gelatinized. However, starch films are naturally brittle, so plasticizers like glycerol are added to improve flexibility. Starch-based bioplastics offer an eco-friendly alternative to single-use plastics and have the potential to reduce environmental impact while supporting sustainable material development.
Several key materials were used to prepare the starch-based bioplastic film. Our main polymer was cornstarch, which forms the base structure of the bioplastic. We added distilled water to create the starch slurry, and we used liquid glycerol as the plasticizer to improve flexibility and reduce brittleness. As the acid catalyst, we replaced vinegar with a small amount of diluted nitric acid, which helps break hydrogen bonds in starch granules and supports the gelatinization process. For the apparatus, we used beakers, a hot plate, thermometer, and a spatula for heating and mixing the formulation. Petri dishes were used for casting the film into a uniform layer, and a drying oven was used to remove moisture from the gel and form the final film. Each material and apparatus played a specific role: starch as the polymer network, glycerol as the plasticizer, nitric acid as the catalyst, and the equipment to ensure controlled heating, mixing, and drying. Together, these components form the complete setup needed to produce and evaluate our starch-based bioplastic.
Film preparation outcome. All starch, glycerol mixtures successfully gelatinized. Films cast into Petri dishes showed uneven thickness. Oven drying caused overheating, burning, and non-uniform drying. Final films were fragile, patchy, or partially degraded. Unable to conduct flexibility, water absorption, and appearance tests due to sample damage. Visual observations. Edges appeared darker, burnt. Center areas remained soft or tacky. Surfaces showed bubbles and cracks from overheating. Films with higher glycerol percent were stickier but still burnt at edges. The starch bioplastic films could not be properly evaluated because the oven drying method caused rapid water loss, overheating, and burning, which led to uneven thickness, cracking, and fragile film structures. Although the mixtures gelatinized successfully and citric acid still acted as an effective catalyst, the high heat prevented the polymer network from forming correctly. The main issue was the drying process rather than the formulation itself. Using thinner layers and allowing the films to dry slowly at room temperature would produce smoother, stronger, and more uniform bioplastic films suitable for testing. How to improve? Cast thinner layers. 1. Spread gel more evenly in Petri dishes. 2. Reduces drying time and prevents thermal stress. Air dry at room temperature. 1. Slower, controlled drying prevents cracking. 2. Produces stronger, more uniform bioplastic films. Adjust oven conditions. 1. Use low temperature, 40 to 50 degrees Celsius, instead of high heat. 2. Check periodically to avoid burning or over-drying. 3. Optionally use a fan or dehydrator for gentler drying. Improve mixing and pouring. 1. Stir longer for homogeneous gel. 2. Remove bubbles before casting. Standardize film thickness. 1. Use a leveling tool or fixed volume per tray.
Despite the unsuccessful outcome, the experiment clearly demonstrated how sensitive starch bioplastics are to processing conditions, especially temperature and drying duration. This finding is valuable because it shows that controlling water evaporation, film thickness, and glycerol retention is essential for producing a functional bioplastic. For future work, we recommend drying at a lower temperature of 40 to 50 degrees for a shorter period.
Thanks for watching.